a little bit here and there.
Here and there. Okay. All right. So, gents, today, as I mentioned before, I am going to be going through Module 7, and I know that we also kind of missed out a few of the things that we wanted to do last session, Module 5, as well as some skills practice. So, we're going to be doing that to begin with. So, the outline that I've got set up for us at the moment. So we're starting at 8 o'clock, and then we'll go back and talk about the next cycle and the effects of it on sea level climate and evolution. And then we're going to go and talk about tools, which I really want to focus on because we didn't get to do a lot of that before, talking about geological timescale as well as something that is. Then we get a chance to do a little bit of uh, practice with some of the skills questions. And then at 10:05, after we've done all of the different skills practices, I'm hoping to have a bit of a break and then we'll rest on at 10 past 10 for module 7 and then hopefully finish by 11. How's that sound? Pretty good? Excellent. All right.
Yeah, it's all right.
Fantastic. Right. So let's just get on to the influence of kind of making sure that we understand the content before we kind of do some of the skills. As you know, this is a skills and knowledge examination you guys are going to be doing. It is going to be more heavily weighted on the skills part, but just like in any kind of science exam or science course, the skills are a way by which you can also understand the content, and then by the same token, um, you can demonstrate your skills by contextualizing it in some context. So there is, even though it is going to be more heavily weighted toward the skills, you still need to have the understanding of the content to be able to show those skills. So let's just do some more of this content here. So we know that the plate tectonic supercycle is a thing that happens, and we know that it is something that is driven by different kind of mechanics and processes. We don't need to go to the detail of that. We've covered that in a lot of detail, not only during our assessment task where we created those models, but we also talked about it, during class as well. So we have a very good understanding of how the mechanics of that works. If you don't want to revise that, please make sure that you do that. But I'm going to focus more on the effects of the plate tectonic supercycle on other parts of our planet. So one of the things that it has a big effect on is sea level. So we know that, just zoom on these for a second. Okay, so we know that when, I just got this from the textbook, by the way. We know that during the tectonic supercycle, as the continents move, there's an increase in the total area of the ocean around the world. So what happens when there's a supercontinent that forms? The supercontinent actually sits a lot higher than like the regular continents that we have now. Okay, so we say that it's a high standing supercontinent. It's high standing because what happens is as the continents collide, mountain ranges form, as we know, and as they form, it actually traps heat of the mantle. Whereas in when there's no supercontinent, the mantle is able to release some of its heat through the thinner non-continental plates, so the other crustal plates that are non-continental. Because when the supercontinents are forming, a lot of that heat is trapped. It causes the continental crust to actually expand, and this expansion is actually significant, and it allows for the supercontinent to be uplifted. Okay, So trapped heat causes the continental crust to expand. It elevates the supercontinent. At the same time, the sea floor, which is older and also colder, will start to subside into the mantle. So essentially, what's happening is there's like this doubling effect. Okay, so it elevates the supercontinent and lowers the sea floor. So as you can imagine, this differential will cause an effect on the sea level. So this causes the sea level to essentially drop. Okay, um, the estimate, these two things combined together, we estimate that the sea level can drop by as much as 400 meters. So sea level at the coastline of the supercontinent is actually at the very minimum. So when we have supercontinent forming, we have very low sea levels. As you can see, we still already have some sort of on for all on the planet. And so let's just have a look at the next one here. Okay, so the other thing that we have to look at then is the flow-on effect on the climate. So the effect of the supercontinent on climate, this was really demonstrated when Pangea, so this was the last supercontinent, um, drifted over the South Pole during the late Carboniferous era, no, period rather. So if you have a look here, some point, okay, all of Pangea, which is comprised of water in South America, Africa, India, Australia, and Antarctica, at some point it actually drifted towards the south. Antarctica still is at the South Pole at the moment. Okay, the other continents have since split up and moved away. But at some point, this big mass actually was toward the South Pole. So this large area, and remember, it's a high standing land, so it's a lot higher than the oceans. It basically experienced very long nights. So at the times where there wasn't much sunlight, as we know, Antarctica will during the winter time have 3 months, 3 months at a time of no sunlight. This was happening to um, this whole southern supercontinent. So when Pangea, sorry, this is Gondwana over here, the Antarctica, Australia, India, and Africa and South America, but this was connected to all the other ones as well. So this is the Gondwana part, okay? So this is the Gondwana part. Because of this, um, a massive ice sheet was formed in the middle of it, which is currently Antarctica. Um, so when Wegener actually proposed his idea of continental drift, this is actually one of the pieces of evidence that he used. He was talking about, the ice sheets that you can trace you trace its boundaries, and you can almost kind of piece them all together when he was showing the ice sheets that you can see. So this is the glaciated regions at the moment in the different continents of Gondwana, and he said that you could um, that it was all together like this before. Okay, and so we know that that's not true. Like he was laughed out of the room when he proposed it before, but we know now that that's true. But this has a massive effect on global climate. It's if this is happening over the South Pole, if it were to occur at the North Pole, similar thing would happen. The positioning of the supercontinent over the North and South Poles is actually a very significant factor the um, in contributing to ice growth. So when Pangea started to break up and disperse at the end of the Permian period, um, there was a lot of geological activity that was happening at the time. Also, we know that there was an enormous amount of magma in Siberia. Um, that was coming up, and so this was made of basalt. It was forming basalt, and so what would happen was the continents would diverge, and it eventually formed the Atlantic Ocean. It also released vast amounts of carbon dioxide as a result of this volcanic activity. This then started a warming. So during the supercontinent, it started to freeze up, okay, because of all of the ice that was forming and the waters were going down. But then when they started to split up, these will then coupled with a lot of volcanic activity, which will then increase the carbon dioxide load. So there's a cycling of the climate as a result of the supercontinents. And we did discuss that before as one of the contributors to this cyclical climate change. We talked about when we were learning Module 7 before, and we'll touch on that again before. So as you can see, there is actually quite a significant effect on the climate due to this plate tectonic cycle. So, some doesn't always have such like huge consequences um, like this, but it does always involve some sort of change to the climate. It will involve significant warming, and different places like the ice house conditions that are around when the supercontinent is present. Now, because of these changes to our biosphere, to our hydrosphere, to the atmosphere, the biosphere is really affected, and this is where evolution comes in. So, one direct consequence of the different land masses coming together is allows for mixing of, I guess, the ability of life to kind of experience very similar kind of conditions and share genetics, across um, different pieces. Uh, so one direct consequence is um, terrestrial flora and fauna will then start to compete with each other. So when we talk about plants and animals living in this particular area, we know that they will have resources that are limited, and so they will have to compete with one another. This will then lead to different kinds of selective pressure starting to appear. When we have um, when we have the continents, supercontinents start to break up, these will then start changing the environments once again. And for the students of biology, you know that the biggest driver of evolution are these selective pressures. So, increase in competition or change in competition, change in the amount of resources that are available, the change in the climate. This all leads to different things that are directing what's going to survive and what's not. Okay, so um, our understanding of evolution stems from the Darwinian theory, where basically it says that adaptations arise, you know, accidentally. I shouldn't use that word. It's not quite accidentally, but what happens is it's random. Okay, so it's a result of random mutation, but the characteristics or the phenotypes that will prevail are the ones that lend an advantage to the individual. So imagine if you have all these living things in a supercontinent and they have a set of survival conditions. If these conditions start to change, not every one of those individuals are going to survive. In fact, a lot of them are going to die out. Okay? They're going to become extinct because they're not suited to the environment. However, those that do have those random mutations that allow them advantage over those that don't will flourish, and they will start to increase in number. And that's when the speciation occurs. Okay, so um, continental dispersal will lead to different kinds of environments, different selective pressures, and so these variations that have been adapted to local environments become supposed to become either extinct or they become dominant in that area. It just so happened that, for example, in South America, And in Australia, we have it's going to make the world's share of the marsupials. It, it just so happens that the marsupials are different from the northern mammals. So marsupials are mammals, except instead of having their young, giving birth to their young, pretty much fully developed because they grow inside of their body using an organ called the placenta. Marsupials don't have placenta. So humans, cats, dogs, elephants, most of the other mammals that are not marsupials have this thing called the placenta that allow them to nourish their babies inside of their bodies until they're ready to come out. So they're called placental mammals. Marsupials are those that they don't have a placenta, but what they do is they give birth to a very underdeveloped fetus, which then comes out, then finds a pocket, okay, so or a pouch. So marsupial actually comes from the Latin marsupium, which means pouch. So in Australia and to some extent South America, the mammals that they have there didn't have a placenta, but their young would go into the pouch, find a nipple, which they will then latch onto, and they will drink that milk and keep growing, and then they will emerge a little bit later on, a bit more developed. So anyway, the point that I'm making is these types of mammals found favorable conditions in South America and Australia. It's also that they outcompeted any other mammals that might have been around at the time. And that's why we have exclusively marsupial native mammals in Australia. Then we have them also in South America. We call this type of evolution adaptive radiation, where things will move outwards, and as they move outwards, they adapt to the situation around where they are. So they're moving away from whatever the norm is in other places. Conversely, the new content positions, pardon me, as I said before, if it doesn't cause things that kind of change, it causes other things to become extinct. Okay, so we know that during times of massive change, so the breakup of these continents, well, actually, this is quoted by the fossil record, that they will actually result in mass extinctions. All right. So those are the three areas that we look at. So sea level is affected, climate is affected, and evolution is affected by the plate tectonic supercycle. Question that may arise, uh, questions that may arise that talk about this might ask you to look at some of the links, for instance, of what can cause changes the in the environment due to the breakup of continents. You might be asked to provide the skill that might be asked is you might have to draw a flow chart. So then what you do is you link the ideas that you have and you draw the flow chart. We'll go through that one. Right. So let's look at information at the moment and geological time. So in this um, I suppose whenever we talk about these kinds of things changing, we need to really talk about the evidence that we have because this is what we're going to be using as our this is our evidence. This is what we're going to be showing as the reason why we have these things, and we're going to be able to justify it using our evidence. So, PowerPoint is yes, I can have a moment. Let's see. Okay. So the point that talks about fossil formation. Basically, we investigate and model the processes of fossil formation by examining a variety of methods or methods in rock, including mold formations, cast formations, and trace fossils. By no means are these the only way, or are these the only types of fossils that we have, but these are the ones that we're going to focus on. So let's just have a look firstly at what they are. So fossils essentially is any preserved evidence of a life from past geological age. So we're talking about here remains or impressions or traces of once living organisms that have been preserved. The evidence has been preserved in rocks or some other substances, amber or some other method, which has then allowed it to stay in a form that we can then study and recognize. So generally, when we talk about fossils, they're older than 10,000 years, and fossils are always going to be some sort of naturally preserved. So, for example, when we talk about the question might come up, mummies in Egypt, are they a fossil? The answer is no, firstly, because it's not quite 10,000 years, and also because it's not so natural the way that it's done. It's used chemicals and it's used processes that are not. I mean, some of it is borrowed from what fossilization uses, but in this particular case, it's man-made. All right. So what we're looking at here is a um, fossil. Okay, this is what we call the mold fossil. Mold is like a hollow, pardon me. So I've got allergies at the moment. There's time to look up. My nose just gets blocked up. Anyway, mold is hollow. Um, and in this case here, it's this here is an imprint of um, of what's living, and it has left its impression or its mold in a bit of sandstone over here. So that's a mold. Cast is, um, as the name suggests, usually it results from an organism. So these here, what you're looking at here, these aren't shells. Okay, these are a cast of a shell, which means that these are just minerals now. These are just mostly silicate materials and other minerals filled in what was once a mold. Okay, so this allanite or whatever this organism might have been, when it died, it got covered over and it formed some sort of mold. And over time, minerals replaced the living tissue. Okay, so it made the cells of this organism, or even replaced the minerals that are found in shells. Calcium or whatever here is replaced by silica. And eventually it hardens into a rock. So this is a cast. Okay, so the cast is basically just a filled-in version of the mold. And the other one that we look at is the trace fossils. And trace fossils are basically just evidence of existence, but it's not direct. Okay, so it's indirect evidence of activities. In this case here, these are footprints. Um, these fossils they can be casts or they can be molds. Okay, so in this case here, we have the cast of prints. This is also the cast of growth of. So these are the fading lines of some sort of invertebrate. And this here is a coprolite or fossil poo. Okay, so the fossilization of like the poo of dinosaurs and other living things, we call that coprolite. And coprolite is actually a trace fossil, and it can be a cast or a mold. In this case here, it's cast of the poo of some past living organism, and it can give us a lot of information the about the living thing. Okay, so these are all different types of fossils. So when we talk about them, let's make sure that you have an understanding of what a mold is, what a cast is, what a trace fossil is. Like I said, there are going to be other types of fossils. If you're interested, if you want to get Band 6, I would recommend maybe reading up on the different types of fossils. I borrowed a lot of my stuff from the textbook as well as from Enrollment. So make sure you have a look at that. I know that they do have a lot of stuff on there. Okay. So we have this evidence from past life. Now we're going to try to link it to our understanding of what are these fossils, how do they allow us to understand the past. I guess for us to be able to understand the past, we first need to know the way by which we measure it, and this is what we call the geological time scale, or GTS for short. Okay, so the geological time scale, you guys will be familiar with the look of it at least. We've talked about the eons before, the eras and the periods. But we'll talk about it in a little bit more detail. It is an important aspect of Earth and environmental science. You will be provided with a time scale that's going to be part of the exam, and you're going to be expected to know how to use it to answer some questions. All right, well, firstly, let's have a look at the divisions that we have here. Firstly, let's have a look at eons. So eons here. So the eons, okay, they're the largest division, okay, and when we look at the eons, we divide it into the this is looking from the oldest, so this is millions of years ago. So this is from 4,500 to zero, okay. So most of them will be shown this way. So the modern time is going to be at the top. Yes. Right. Beg your pardon. Okay. So the Hadean, the Archean, and the Proterozoic, these are grouped together. We usually call them the Precambrian. Okay. Precambrian meaning before Cambrian. Why is it called Precambrian? Well, if you have a look at where the Cambrian is, it's going to be basically starting above where. So this is the Paleozoic. I will talk about the era, but the Cambrian period occurs after the Proterozoic here. Okay, so this is what we call the Precambrian eons. Then the Phanerozoic has, so this doesn't have a whole stack of variety in the fossils. Yes, there's fossils in them. Not a lot from the Hadean. We don't expect there to be. Why not? Because it was before life was around. The Hadean was when the Earth was still kind of cooling down. It was during the time where there was not a lot of life. Well, there was no life yet. There was not a lot of, I guess, places for things that will for life to occur. Okay, but this is when operate and how they have they suggested that this is when the molecules of life may have formed on Earth. Okay, so this is the Hadean era. The Archean, this is where we start to see a little bit more, but these are all still very ancient type of life. These are very simple. These are your your archaebacteria, your extremophiles. They will be around during this Archean era. Okay, so as we go the list, it becomes more and more complex, I guess is what we're trying to say. Okay. So it says here that, we have the Precambrian era is anything up to about 550, 600 million years ago. Okay. And then we'll have a look now. So those are the eons. Okay. So we technically, we're in what we say the Quaternary period. We are part of the Cainozoic era, which is part of the Phanerozoic eon. Okay, Phanerozoic actually has a more comprehensive fossil record, but we divide it up a little bit more. These take up a lot more time, but it's very, very simple. This doesn't, it's only in the last 550, 540, 550 million years, but it's been broken up into more sections because of the different types of life that were around during this time. And essentially, these are what the periods are. Periods are basically a snapshot of what types of life are around during that time. What were the dominant types of life? So eras, eras or eras, it doesn't really matter how you say it. Um, they usually are marked, so the beginning and end of them are marked by major changes in the fossil record. We talked before about the Cambrian explosion. Okay, because the Cambrian explosion happened during the Cambrian period. We call it the Cambrian period, which occurs in the Paleozoic era, which is part of the Phanerozoic eon. Okay, so the Cambrian period, this starts basically the life as well. It leads to the life as we know it now. Okay, so this is when we started to see all of these multicellular organisms just explode in number. So previous to that, the Ediacaran, so the Ediacaran would be found just Precambrian, so will be in the Neoproterozoic. So this is where you would probably find the Ediacaran. But the Cambrian period will then start all of this life here. So each of these periods will be marked by special fossil groups. So, for example, the Devonian, okay, this area here, this is what we call the age of fish. Okay, so the Devonian is where we would find a lot of fossils that are, fish-like. But then when we move up to the Carboniferous period, which that is then further divided into the Mississippian and the Pennsylvanian, um, this is when major coal deposits were put down. But we understand that this is when trees would have started to come about because of the emergence of this new type of molecule that was developed, like cellulose. Okay, so cellulose is a molecule that was developed by trees to form lignin. That will then this lignin allowed for trees to grow taller and higher. Bacteria couldn't break them down, so when they died, they got buried and got turned into coal. So during this era, or this period rather, is when a lot of our coal was formed. So there are smaller age groups that are not shown here, so we call them epochs. Okay, so epochs are smaller divisions. For example, human civilization. So the human civilization would be found like even a smaller kind of part of the Quaternary. Um, so agriculture and permanent settlements occurred since the end of the last ice age in the Holocene. Okay, so if we have a look here, okay, so the Cambrian period here, okay, the Quaternary period is here, and we're kind of like not even visible here yet in terms of when we started to come about. So this um this diagram here on the right. So this here, okay, so these are what we call the index fossils. Right? The index fossils are fossils that are used to signify a particular period in time. Okay, so index fossils are useful because they allow us to tell when a particular um, piece of rock is formed. If we find a fossil there, we can judge its age. So index fossils are distinctive and easily identifiable and very commonly found during that time. Okay, they usually live for only a very short period of geological time. They have a short range, but they're distributed over a large region of the Earth. This is useful because it allows us to pinpoint when this rock was formed. Now, if you were to use a fossil that was around for a long period of time, it's not going to be useful as an index fossil, okay, because it's not going to tell us exactly what it was. Whereas if something that we know definitely lived only during this particular time, it's easier for us to tell when this rock was formed, when this would have been buried. Uh, okay, so rocks from one area, sorry. So age of rocks can be determined based on the presence of an index fossil or a group of index fossils, so that rocks from one area can be correlated or matched to rocks of the same age from one location of rock of the same age in another location. Um, Usually, the first appearance of key index fossils mark the divisions of the geological time scale. So this is what correlation is. So we use the two ideas of log superposition and the lower formal succession to be able to tell the age of rocks. Um, as you can see the Enrolo watermark there. I just looked this from Enrolo. You can actually have a look at this there. But basically, fossils appear, we know, in a predictable order. We know that simpler life forms are around older, so they'll be found. Low superposition tells us that things are layered from bottom to top. So oldest are at the bottom, youngest are at the top. Okay, so if you find something down the bottom, okay, you can be pretty much assured that it's very, very, very old. Unless uplifting or any sort of intrusion or anything else happens, any kind of geological activity that disturbs the layers, it's pretty much it's pretty much a given that the higher the levels are, the younger they are, because things are deposited on top of one another. So fossils appear in predictable order, even when fossils are found in different locations. Once a fossil has gone extinct, it can't then reappear in younger layers. Um, so layers that contain the same fossil are the same age when combined with other stratigraphic principles, for example, superposition. We know that we can work out what the relative age is. And relative age or relative dating or correlation talks about comparatively what is the age of this comparative to another layer. Okay. Um, Older fossils are found in lower layers, younger fossils are found in higher layers. For example, here on the blue layer, okay, so you're looking at the blue layer here, we can see that sorry, the blue layer here, we can see that the starfish are probably, well, they're not probably, they are the youngest in in this kind of rock strata. The night or the peak layer over here, okay, you can only see it in on this rock, but that doesn't mean that it doesn't exist. Um, it means that if you were to have if you were to have had that in this area here, it would lie in between these two. Um, we're gonna then have a look at the idea of geological dating methods. So geological dating methods is not when earth scientists go out for coffee. Geological dating methods. So when we talk about geological dating methods, it's the use of things such as relative dating techniques as well as radio isotopes to be able to work out the evolution. Use it to kind of date things such as the evolution of things when extinctions happen, and give it like a date, a number date. So to be able to talk about the geological dating method, we need to understand the idea of half-life. Just put this video up. I know we talked about it in class before, but I'm sort of put this video up so that we can get an idea.
The carving of Mount Rushmore was completed in 19...
Can you guys hear that? Yes,
Yeah.
no, maybe.
Yep.
Excellent.
Yeah, we can.
Okay, excellent.
41. But the rocks it was carved into were completed quite a bit earlier than that, 1.7 billion years ago. How does a geologist know that? And how do they know that the Earth is 4.5 billion years old? The answer is a technique called radiometric dating, which lets us tell the age of certain types of rock. Radiometric dating relies on the fact that certain elements have what are called isotopes. These are versions of the atom with extra neutrons in them. Each radioactive isotope decays at a consistent rate. These measurements give us something called the half-life, or the amount of time it takes for one half of the isotope to decay. When an isotope's half-life is up, half your original element will be gone, transformed into a different isotope. Another half-life and you're down to a quarter of your original amount. A half-life after that and you're down to an eighth, and so on. The length of a half-life is different for every isotope. If you wait for enough half-lives to pass, you'll have a hard time detecting any of your original material. So to date something relatively recent, you want an isotope that decays quickly. To go older, you want an isotope that decays very slowly. The term carbon dating refers to dating using carbon-14, which we mentioned earlier. It has a half-life of 5,700 years, and most of it will be gone by about 50,000 years. To date things that are older than that, you want an isotope that decays very slowly. Uranium-238 has a half-life of 4.5 billion years, so it can be used to date things as old as the solar system itself. How do we use this to get the age of something? The unstable radioactive element that you use is called the parent, and the stable, happy isotope you end up with is called the daughter. Dating only works if the only source of the daughter isotope is the decay of the parent. You also need a rock that behaves a bit like a sealed time capsule, preventing daughter isotopes from leaving and keeping new parent isotopes from wandering in. That way, if you end up with half daughter and half parent isotopes, you know that one half-life has gone by, since the rock kept everything locked into the same place. Certain minerals form a tinker toy-like cage around any larger isotopes. This locks everything in place and makes for an excellent time capsule. Zircon crystals, for example, can trap atoms of radioactive uranium inside them, as well as its daughter isotope, lead. So, measure the proportion of uranium to lead in a zircon crystal, and you can figure out when it must have formed. Take this tiny zircon, for example, which would fit comfortably on the head of a pin. Believe it or not, this tiny zircon, which comes from Western Australia, is the oldest piece of Earth we've ever found. It's an absolutely mind-blowing 4.4 billion years old, and comes from when the Earth was only 150 million years after its formation. The zircon was dated using two different isotopes of uranium, uranium-235 and uranium-238. This provided a built-in cross-check, as you had two different clocks keeping time within the crystal. Whichever clock you look at, they give the same result. The uranium's been trapped in that zircon since it formed 4.4 billion years ago. Most dating techniques only work with certain types of rock. You can tell when lava erupted, for example, but can't figure out when sandstone formed. That's because the sandstone doesn't trap isotopes in the tinker toy-like cages that we mentioned earlier. Because there are other ways to tell how old things are in the world, we can compare those results with radiometric dating and show that they match. Trees, for example, put down a new ring each year they grow, and you can count backwards and figure out how old the tree is. You can also use carbon dating to figure out how old a particular ring on the tree is. Just like trees, ice in the Antarctic lays down a new layer each year, creating a similar ringed pattern. We can then compare that to the dates given by rocks trapped in the ice and show that they also match. If radiometric dating weren't reliable, we'd see differences between the results generated by it and those generated by these other methods. Fortunately, radiometric dating is reliable, which means if we go to Mount Rushmore, we know we can touch rocks that are 1.7 billion years old.
Okay. Pardon me. So the geological dating methods of absolute dating. So that's what we call absolute dating. Absolute dating is being able to put a date on something. Relies on the on isotopes and our understanding of their decay. So essentially what it's saying is if you know what the decay rate is of a particular isotope, if you find a rock that you know locks in the isotopes, the parent isotope and the daughter isotope, so there's no movement in or out, then you can then compare that to an index of some sort and be able to work out how old it is. Okay, and if you couple that with your relative dating techniques of looking at layers of rock, looking at superposition, we can then get we can start to put dates on the age of different fossils. Um, okay, just go to okay. So I actually want to do a little bit of skills practice here. Um, I was going to talk a little about uniformitarianism, but we're going to run out of time, so I'm going to kind of skip that and maybe get you guys to read up on it in your own time. But I want to skills practice here. I want to do some um, exercise using fossil identification and interpretation. So, all right. So let's. This is a question that might appear. Okay. Firstly, what kind of a fossil are we looking at here? Somebody, anybody, what kind of fossil? So we're talking at types of fossils. There's cast, there's mold, there's trace. What is it? Let's go.
Would wouldn't be
Hamish.
trace, wouldn't
Trace.
it?
It is a trace fossil and is it a cast or is it a mold?
Mold.
It is good. It's a mold fossil of a footprint. Okay, so it's a trace fossil and the mold fossil. Okay, so it says here the picture shows a fossil human footprint at Lake Mungo, dated at 20,000 years old and 20 Ka. Showing at least 3 stages, draw a flow chart to describe how this fossil was formed. Now, if you guys have got a piece of paper or something around you, I'll give you guys like 5 minutes or so to just kind of sketch what you what kind of flow chart you would do, and then I'll show you guys what the sample answer is, and then we'll talk about what makes it a good answer. Okay, so can you guys do that? Spend 5 minutes, just draw yourself a flow chart showing at least 3 stages of how this fossil may have formed. Okay. Give me that 5 minutes. It's 8:48 now, 8:53. I'll go back to you guys. Excuse me, I'm just gonna go blow my nose again. Feel free to ask questions at this time, by the way, if you need any clarification on what you need to be doing for this. another couple of minutes. Normally for this kind of question, you will have about 10 minutes, but I'm just kind of trying to speed it up a little bit. All right, just we'll just stop there for a second. So let's just break this question down for a sec. So it says here to draw a flow chart. Now it's really important when especially for a skills exam, that we are focusing on the skills that you're going to be showing here. You need to know that a flow chart should show a movement of processes from one to another. So what are the most common parts of, do you think, of a flow chart? Let's go, Daniel. What do you think is important? Firstly, that indicates that something is a flow chart. What do you need to have?
Well, you got to have like one step at a time, and between each step, you got to have arrows like showing the leader where to read.
Excellent.
Between.
Okay, so that's exactly what we need to do. We need to have some sort of showing different steps or different stages, and we need to show the flow of movement from one to the other using arrows. So very important. So those are the features that you need to show. Okay, so let's have a look at what the sample answer here looks like in the marking guide. So in the marking guidelines here, to get the 4 marks, you need to have to draw a flow chart with at least 3 stages. You need to put steps in the correct sequence and provide appropriate information. And that's what they say is going to be worth 4 marks. And I know it's a little bit confusing because there's like, oh, what? There's just 3 points here. How's that 4 marks? Well, basically, they start from the idea that 4 marks shows you this completely. Okay, so if you can draw a flow chart with at least 3 stages, put steps in correct sequence, provides appropriate information, that will just give you 4 marks automatically. All right. And it starts to go down when you're missing some of this. So 2 to 3 marks is if you draw a flow chart. Now, whether it has 1 stage, 2 stage, well, can't really be a flow chart with 1 stage. That's 2 stages or 3 stages. If it's not quite in the correct sequence, but you can tell that it's a flow chart. Then, depending on how much information is on it, they'll give you 2 to 3 marks. Like I said here, any type of relevant information is 1 mark. I've got to stress this, guys, in an exam, even if you just rewrite the question, I know that a lot of teachers will kind of say, don't do that, don't do that. Well, I'm going to tell you, if you rewrite the question, for me, that is engaging in the topic, okay? And if you've engaged in it in some way, that it's better than leaving it blank, okay? So I'm not going to say necessarily that you're going to get a mark for it, but if this was like if it was a 1 mark question and you rewrote the question, you're not going to get anything for that. That's not relevant information. But if it's a 4 mark question and you really don't have any idea at all, do something. Or write down a couple of words, okay? Or even draw boxes that have arrows that are pointing, to each other or whatever. Any kind of relevant information is going to give you a 1 mark. I'm not saying that, that you resort to this all the time. What I'm saying is do not leave any questions blank. Okay? If you leave it blank, the maximum you're going to get for that is a 0. If you do anything, I'm not saying you're going to get a mark for it, but the minimum you're going to get is 0. Okay, and there's that slight difference there. The maximum you'll get for not writing anything is 0. The minimum you get for writing anything is 0. Okay, so simple answer. First step: 20,000 years ago, a human walked across sand or clay on the surface of Lake Mungo. Okay, so this is relevant information, and it is appropriate information because there needs to be some sort of sedimentary, um, surface that they walked on because you're
So
leaving impact. Yes.
do you have to like provide the information like the 20,000 years ago in Lake Mungo and stuff?
I wouldn't necessarily have to.
Or
I
can you just say that a human's walking across the lake and steps in soft
Okay. Very good
sediment?
question. There's actually the answer to this is you will get marks. You will get marks even if you don't include that information. But I want you guys to get into the habit of using the information from the source. Anytime you're given any sort of stimulus material, take it for granted that the marker wants you to refer to the information that they're giving you. Put it down to ego or whatever, but the examiner, the person who wrote the exam, wants to know that you are actually engaging in the stimulus material properly. Okay, so err on the side of caution. If you have been given information, explicitly mention that information. Okay, so the picture shows a human fossil print at Lake Mungo, dated at 20,000 years old. Lake Mungo, they've mentioned it. 20,000 years old, they've mentioned it. They didn't need to say that. Okay, they could have said the human footprint in mud, from a while back. If they'd said that, then you wouldn't need to say Lake Mungo, but they put that there, so use it. Does that make sense?
Yeah, just
Yeah. Yeah. Okay. So the next step is the wind blows sand or clay and covers the footprint with layers of sediment. Okay, so this is important. Okay, so you need to be able to say that sediment covers it up, and then layers of the sediment are removed by wind or water, exposing the footprint. So you had 3 steps here. You could have added other steps, including compaction, hardening of the sediment, any of that kind of stuff, and that would have been good too. But in this case here, you've given us the 3 steps that allowed us to talk about how this fossil was formed, and yeah, that's good enough there for the 4 marks. Any questions on that one? Nope. I'm gonna apologize, gents. My allergies are just getting worse and worse, and I'm finding it really difficult to actually talk now. I'm gonna take some antihistamine, and I might actually go and see if I can. I don't know what I could do in here, but I'm not. This is not going to be quality presentation for you guys. I'm just going to be sneezing and spluttering all over the place. What I'm going to do, so I've got a few more questions that I want to go through. What I'll do is after I've taken my antihistamine and whatever, what I'll do is I'll record what it was that I wanted to go with you guys, and then I'll post it up on Canvas. I've already posted up last session one, but I'm gonna let you guys go early. It's just I'm not gonna be able to continue like this. So I've recorded this part, and then what I'll do is I'll record the next part and post it up later today. Is that cool, guys?
yeah, that's all
Yeah,
good.
righto. Yep, all
All right.
good.
Sorry, guys. All right. Well,
good.
good. I'll let you guys know when it's up on Canvas, and then I'll if you have any questions or anything if you've got any notes or any kind of questions that you've gone through that you'd like me to have a look through, please don't, pardon me, please don't hesitate to send it through. All right, gents?
Yeah.
Yeah,
All
sweet.
right.
Yeah.
Cheers, sir.
I'll see you guys.
Thanks, sir.
Thanks.
Bye-bye.
Good one.
Sir.
Cheers, sir.